Hey everybody, this is your lecture on expanded octets and VSEPR, VSEPR, and we'll get into that definition in just a few slides. Please follow along with your own lecture slides, and anytime that you have a question, write them right on the slide. They pop into your head, and ask those either by emailing, coming to office hours, or asking them in class. All right, so expanded octets are really just Lewis dot structures, but certain atoms can expand their octet, meaning they can have more than 8 electrons in their shell. So the steps that we will follow are the same as what we were following for regular Lewis dot structures, but when we get to the very end, we will have more than 8 electrons for certain atoms, and that is totally fine for atoms that are in periods 3 or higher to have more than 8 electrons. All right, let's walk through this. And first step, I already did for us for both examples. I calculated up the total number of valence electrons and total number of valence electrons over here, just based on their location on the periodic table. Then I drew out the skeleton structure with the least electronegative atom drawn in the center and the more electronegative atoms around the outside. And the whole goal is to keep the most symmetrical shape as possible. And we'll get more into exactly why that is in a few slides as well. Now we'll start distributing the electrons, and we will first, or not distributing the electrons, we will first start using those valence electrons by connecting the central atom to the outside atoms with a bond. And recall that each bond formed has 2 electrons. 2, 4, 6, 8, 10. And we can already see how phosphorus has exceeded its octet. We wouldn't be able to form a bond with all these chlorines unless phosphorus expanded its octet. And we can double check by looking at the periodic table to make sure phosphorus can do this. It's in period number 3. Therefore, since it's not in 1 or 2, phosphorus does have the ability to expand its octet. And I know that chlorine wouldn't be the one to do this just because phosphorus is in the center, since it is the least electronegative element. That is why it ends up being the one that expands its octet. All right, but we still have 30 more electrons to place. So let's put those in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So 40 total electrons, and the expanded octet is on phosphorus. All right, let's look at xenon difluoride. So first, connect the central atom to the atoms on the outside with a bond, and that bond accounts for 2 electrons each. So we've used 4 total electrons. Now we'll distribute the electrons to fluorine. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I've used 16 of my 22 valence electrons. So I have 6 more that I need to place, and I will not be able to place them or any more groups on fluorine. The reason why is because fluorine is in group 2 on the periodic table. Therefore, it cannot expand its octet. So xenon will get those remaining 6 electrons, and it's okay that xenon does because xenon is in group 5 on the periodic table. Therefore, it is after groups 1 and 2, or periods 1 and 2, sorry. 1, 2, 3, 4, 5, 6. All right, so we have used all 22 valence electrons with 6 extra electrons placed on xenon because it is in period 5 on the periodic table, and it is allowed to expand its octet. All right, now that we know how to draw out the dot structures for atoms that have expanded octets as well as ones that follow the octet rule, we now are going to start naming these different shapes. And we will do that with the VSEPR theory, which stands for valence shell electron pair repulsion. Okay, so it's just a method of naming these different shapes, and they have different names because of the different orientations that they form. Because right now we've only been drawing two-dimensional shapes, whether on paper or on our iPads, but in real life, these shapes or molecules are three-dimensional. So we need to start naming those three-dimensional shapes. So what VSEPR is based off of is the Lewis dot structures, and it focuses on the repulsion of the electron groups to maximize the separation of them. And I skip down and talk about what the electron groups could or can be, and they can be anything with electrons. So electron groups can be lone pairs, single bonds, double bonds, triple bonds, multiple bonds, or even just a single electron. All of those can be qualified as an electron group. And when we've been saying to draw your compound or your molecules as symmetrical as possible, that is because we were thinking ahead to this VSEPR theory. Because electrons have negative charges, which we already know, and charges or like charges repel each other, that means that drawing the most symmetrical atom or symmetrical molecule is following this fact that electrons are not attracted to each other. They repel each other, so they want to be as far apart as possible. Okay. So first we're going to look at geometries when all of the groups surrounding the central atom are bonding. Okay, and this creates 5 basic shapes, and we will call this electron geometries. We also have molecular geometries, which will be when we have atoms that have lone pairs surrounding them. Okay, so lone pairs have really high they have really high negativity because we have 2 electrons right next to each other. They're not bonded to anything. They're not distributed. So there's a lot of negativity surrounding lone pairs. This causes other electron groups to be pushed further away from those. Okay, so let's look at our VSEPR chart. And I believe this slide is the very last one on your lecture slides. So right here we have the electron geometry, which this is just based off of all of these pictures, which indicates that we have, for linear, 2 electron groups coming off of that main atom, 3 electron groups for trigonal planar, 4 for tetrahedral, 5 for trigonal bipyramidal, and 6 for octahedral. When we have lone pairs that are off of our central atom, this ends up changing the shape a little bit. So you guys can see here. Because the shape is changed, or the geometry is changed, we also have to change the name. When there are no lone pairs coming off of the central atom, our electron and molecular geometries end up being the same, which is really nice for memorization purposes. But when we start to have lone pairs, the names change a little bit, and they try to reflect the shape that they are formed. All right, so let's look at the example from earlier, and right there, electron and molecular geometries. So first one, PCl5. Phosphorus has 1, 2, 3, 4, 5 electron groups coming off of it. Therefore, if we look at our chart, 5, we have trigonal bipyramidal. Since none of those are lone pairs, that means that our molecular geometry ends up being exactly the same name. Now, for xenon difluoride, there are 1, 2, 3, 4, 5 groups again, 5 electron groups again coming off of that central atom. So our name doesn't change. Okay, I know these look a lot different, but we still have 5 groups coming off of the central atom. So only thinking of electron groups, the electron geometry is the same. But when we get to the molecular geometry, then this ends up being a lot different. So we have 2 bonds, and 1, 2, 3 lone pairs. Back here, 2 bonds, and 1, 2, 3 lone pairs. This will be linear shaped, or have a geometry that is linear. Back from class on Monday, we did phosphorus trichloride as an example. And in this diagram, there are 4 electron groups coming off of phosphorus. This makes the electron geometry tetrahedral, but because we have a lone pair, that means that our molecular geometry ends up being trigonal pyramidal. I'll put those in the same colors as before, or on the last slide. All right, so to sum it up, here is the VSEPR chart, and this is something that you guys will need to memorize, but I want you to try to look for patterns on here. So your electron geometry will always have the same name as the molecular geometry that has no lone pairs. Okay, those two, oops, see if that makes a nice square. Yeah. Those two will always be the same and just based off of how many electron groups are coming off of the central atom. For the other molecular geometries, if you look, you can see some type of patterns. So from 3 to 4, you have bents, and you have 2 linears, T-shapes. So there are patterns that you guys can look for and similarities, all based on how the electrons are pushing, or the electron groups are pushing in different ways based on how much negativity that they have. And what we've done in the past is given a blank electron geometry sheet like this, so that right when you get your test, if you want to write down all of these, you can do that. All right, let me know if you guys have any questions. Thanks for watching.